Diagonalization. In this lesson, we discuss diagonalization of a matrix using an eigenvector basis into a matrix of eigenvalues. Special attention is given to symmetric matrices. Suppose that x1 is an eigenvector of the n by n matrix A, corresponding to the eigenvalue lambda1, and that x2 is an eigenvector of A, corresponding to the eigenvalue lambda2. Continuing in this way, suppose that xn is an eigenvector corresponding to the eigenvalue lambda n. This gives us a system of equations where x1 through xn are column vectors. We can rewrite this system of equations in matrix notation. Recall that the eigenvectors are column vectors. Perhaps this explicit notation is a little cleaner. Note that the eigenvector matrix on the left-hand side is right multiplied by the diagonal matrix of eigenvalues to distribute the eigenvalues to the columns. Left multiplying the eigenvector matrix by the eigenvalue matrix would have distributed the eigenvalues to the rows. Let's call the eigenvector matrix S, and the eigenvalue matrix lambda. Then A times S equals S times lambda. Furthermore, if the matrix S is invertible, then we can decompose the original matrix A into S times lambda times S inverse. This rather remarkable formula, called the diagonalization of matrix A, says that A is similar to the diagonal matrix lambda, using the basis of eigenvectors in the columns of S. Because lambda is a diagonal matrix, the variables are completely uncoupled in this basis. This can really simplify a problem. Recall the lesson on non-standard bases. Matrices are similar if they have the same action in different bases. The matrix A stretches and rotates the sheep, but, in the basis of the eigenvectors, the sheep is merely stretched along the basis. We change to the eigenvector basis by applying S inverse. We stretch the eigenvalues in our new basis, and we change back to the standard basis. As you can see, all the action happens in the eigenvector basis, in a rather simple and meaningful way. Let's look at an application of diagonalization. If we square the matrix A, we multiply the right side by another S lambda S inverse. The middle two terms cancel, and after multiplying the two diagonal matrices of eigenvalues, we are left with A squared equals S lambda squared S inverse. Of course, by induction, we have a similar expression for any power of n. Keep this formula in mind. Let's look at the exponential operator e to the a. To evaluate this, we'll start with Taylor's series. Here's the Taylor's series expansion of the scalar exponential function. The same series applies to matrix exponentials. We now have powers of a. Replace the powers of a with their diagonalizations. Now factor out an s on the left and an s inverse on the right. The sandwiched expression is the Taylor series expansion of e to the lambda. Lambda is a diagonal matrix, so it scales each eigenvector basis independently. That means that we can apply the exponential function to each of the diagonal elements independent of the rest. We can use this formula to solve a system of differential equations. Suppose that we have a system of differential equations. We can write this system in matrix notation, which, in shorthand, says that the derivative of a vector x equals a matrix A times x. As in the scalar case, this linear problem has the solution, x at time t, equals the exponential of ta applied to x at time 0. We can replace the exponential operator with its diagonalization. The solution to the original problem simply involves its eigenvalues and eigenvectors. We substitute in the values from the original problem, and simply get this solution. Now, let's take a step back. Multiplying both sides of the equation by S inverse is the same as making a change of basis. By changing to the eigenvector basis, we have decoupled the solution. This is rather remarkable. By changing to the eigenvector basis, we have in fact decoupled the problem into a system of independent differential equations. Physically, this isolates the behavior into pure vibrational, growth, and decay modes, with frequencies and amplitudes given by the eigenvalues. Let's now look at the diagonalization of symmetric matrices. Symmetric matrices have two important properties. Their eigenvalues are always real and their eigenspaces are always orthogonal. Because of this, a symmetric matrix A has a special diagonalization. The matrix of eigenvectors can be replaced by an orthogonal matrix Q. The inverse of an orthogonal matrix is simply the transpose of the matrix. So, A equals Q lambda Q transpose. This formula is known as both the principal axis theorem and the spectral theorem. Let's see why. We start with the principal axis theorem. Let's examine the diagonalization of this matrix. The matrix has the eigenvalues 4 and -1, with orthogonal eigenvectors along the 2, -1 and the 1, 2 directions. So, we can write A in terms of its diagonalization using the rotation matrix Q. As before, let's look at the effect of the matrix A. Notice that the eigenvectors of A are perpendicular. We start by applying the rightmost matrix of the diagonalization. This matrix rotates the sheet by approximately -27 degrees. We could alternatively think of the matrix as a change of basis operator. Now we apply the eigenvalues, first stretching by 4 in the x direction, and then by -1 in the y direction. Finally, we apply Q, which rotates us back by 27 degrees. Notice that the major and minor axis of the ellipse are along the eigenvectors. This is true for all symmetric matrices, and hence the name, the principal axis theorem. Now, let's look at why the diagonalization of a symmetric matrix is also called the spectral theorem. We can rewrite A equals Q lambda Q transpose explicitly, in terms of the columns Q1 through Qn of the orthogonal matrix Q. The column vectors of a matrix, that is right multiplied by a diagonal matrix, are multiplied by the corresponding diagonal elements. Now let's multiply these two block matrices together. We get this sum. You may recognize the outer product terms in the series. Let's make it a little easier to see what's going on by dividing each term by the inner product of columns of Q. Remember that the columns of Q are orthonormal, so the inner products are just ones. You should be able to recognize each term in the series now. They are simply the orthogonal projection matrices onto the columns of Q, that is onto the eigenspaces of A. This is the spectral decomposition of A. For example, here's the spectral decomposition of the matrix 3, 2, 2, 0. We'll end this lesson by stating that not all matrices can be diagonalized. For example, consider the matrix A equals 1, 1, 0, 1, which describes shearing in the x direction. The characteristic polynomial for this matrix is lambda -1 squared, so the matrix has one eigenvalue of multiplicity 2. But when we look for the null space of A-1I, to get the eigenspace, we find that the matrix A has only one eigenvector. So we can't form an invertible matrix of eigenvectors. Only matrices with a full set of eigenvectors are diagonalizable. Matrices that do not have a full set of eigenvectors are called defective matrices.